Now the next point, that the kinetic molecular theory of gases. Now here we will see its postulates or that assumptions. Now kinetic molecular theory is actually here, it is the theoretical. Okay, so this is the theoretical model, and this theoretical model is applicable for explaining the behavior of that gases. Okay, now kinetic molecular theory, they have given certain assumptions or that postulates. Now look here one by one. This is the first. All gases consist of tiny particles, and that the tiny particles called as here molecules. Okay, this is the first number one assumption. Now second one is what? The actual volume of gas particles or actual value of that gas molecules is negligible, because the gas particles are very small, and that's why the actual volume of the gas molecules is negligible as compared to the total volume of that gas. Okay. Now the third one, at ordinary temperature and pressure, the attractive forces between the gas molecules, that is negligible. Do you understand? At ordinary pressure and temperature, the attractive forces, interaction between the gas molecules are very small, that is negligible, and that's why the gases are easily expanded. Expansion of gas is easily takes place. Now in second case, we have already seen that actual volume of gas is very negligible. So that's why gases are easily compressed. Gases are compressible. And here in third one, gases are expansion takes place. Now the fourth one, the gases molecules are always in continuous random motion. Do you understand? Gas molecules always continuous random motions. They can move continuous. Okay. Then again the random motion. So this is, and they collide with each other. When they are continuous in random motion, that time they will be collide with each other, and also the collision takes place with the walls of container. Do you understand? So collision takes place. Now the fifth one, pressure of gas is due to the collision. Okay, the pressure of gas due to the collision of that gas molecules takes place. So due to the collision of gaseous molecules with the walls of container and with each other, so that time pressure of gas is developed. So that pressure of gas is here. Now collision of gas, next one, sixth one, collision of gas molecules is perfectly elastic in nature. You understand? Gas molecules is the collide with that. The gas molecules collision with the walls of container, but that the collision, this is perfectly elastic in nature. You understand? So therefore, total energy of gas particles is remain constant. So no change in energy during that collision. After collision means there after collision, so total energy of that gaseous molecule not change. So total energy of that gaseous molecule is the remain constant. So this, now the seventh one, average kinetic energy is directly proportional to its absolute temperature. You understand? This is in the seventh assumptions. So in gas, here that is the molecular theory, kinetic molecular theory. In this given, they have given the total or average kinetic energy of that gas molecule is directly proportional to temperature. We know that as the temperature increases, what happens here? As the temperature increases, the collision rate also increases. Do you understand? So its kinetic energy is also increases. Kinetic energy is depend upon that temperature. Therefore, average kinetic energy is directly proportional to the absolute temperature. And the kinetic gas equation, and this is the extra point. This kinetic gas equation is equal to what? Is nothing but PV is equal to 1 by 3 m u square. M into u square. What is m? Mass of that gas molecule. N is number of moles of that gases. Okay. U is velocity of that particular gas molecule. So here V is what? V is the volume of that container. Do you understand? and P is the pressure of that particular gas. This is way of. Now the next, deviation from ideal behavior. Deviation from ideal behavior means what here? The real gases and ideal gases. Yeah, these two terms here actually. The real gas deviates from the ideal behavior. Okay. Now here we know that ideal gas is what? Those gases which obey, strictly follow the gas laws. Okay. They obey this, the general gas equation, ideal gas equation. You know that the PV is equal to nRT. Okay. So from this N is equal to what? PV upon RT. Do you understand? If N is equal to 1 mole, that time PV upon RT is equal to 1 at all temperature. And such gases that I called as ideal gas. Do you understand? Now this way, this is ideal gas for that condition. They strictly follow this is ideal gas equation or then the gas laws. Now if the gases does not obey ideal gas equation, you understand? So such gases is called at that time real gas, or this is real gases. Do you understand? So if the gases does not obey ideal gas equation, that time what happens? This ratio PV upon RT, that ratio is less than 1 or at time greater than 1, but it is not equal to 1. So these gases that time, that is the real gases. Okay, let us study, that is comparative study. Okay, ideal gas and real gas is what? How they have differ with each other. We know that ideal gas, those gases which strictly follow the gas laws, strictly follows, that is Boyle's law and Charles law. This is first the related with that points of that ideal gas, strictly obeys Boyle's and Charles law. Boyle's law and Charles law. But real gases does not obeys. Do you understand? The Boyle's law and Charles law, but it obeys. Okay, it real gases obey, but at specific condition obeys Boyle's law and Charles law at low pressure and high temperature. Do you understand? Now, second one is molecules are perfectly elastic in nature. Now, in real gases, the molecules are not perfectly elastic. Do you understand? Now, the third in ideal gas, no attractive or repulsive force between that gas molecules. No attraction or repulsion between gas molecules. This is just consideration in the ideal gas molecules. Okay, so no attraction, no repulsion between that gaseous molecule, and therefore no loss of kinetic energy. Do you understand? So during that collision it takes place, but no loss of kinetic energy. So in collision, this is the third. Here in real gases, intermolecular interaction present. Intermolecular force of attraction is present. Therefore, hence collision takes place with loss of kinetic energy. This is the real gas. Now the ideal gas, actual volume of that gas molecule is negligible as compared to the total volume of that gas. This is fourth one. Actual volume of gas molecule is very small, is negligible as compared to the total volume of that gaseous molecules. Do you understand? So single gas particle molecule is very small. That's why its actual volume is negligible. Now in fourth one is here real gas. Actual volume of that gas molecule is not here negligible, because in real gases the gas molecules are just hard, spherical, particle. That's why that single molecule also having that the significant volume at high pressure and low, that is temperature. At high pressure and low that particular temperature. Okay. Now the fifth one. It cannot liquefy even at low temperature, but continuous obeys Charles law and occupy the particular volume is zero volume at minus 273 degrees Celsius. So ideal gases cannot liquefy easily at that particular low temperature, but it continuous obeys the going on following that Charles law, and finally what happens? They occupy zero volume at minus 273 degrees Celsius temperature. Here real gases undergo liquefaction at low temperature when cooled and compressed. Now the sixth one, such ideal gas does not exist. You understand? But the real gases exist in nature, like that hydrogen, oxygen, nitrogen, carbon dioxide, helium. This is all that the different gases are available in nature. That is the real gas. Okay. The next one is real gas shows deviation from the ideal behavior at high pressure and low temperature. They are given two reasons why the real gas deviates from that ideal behavior. First one is intermolecular attractive force are not negligible in real gas. We cannot neglect the intermolecular force of attraction in real gas. We know that in real gases like hydrogen, oxygen, nitrogen, the intermolecular forces are present. Our second reason is what? At high pressure, the molecules are very close to each other. We know that at high pressure, increase the pressure, molecules are come close to each other, and that's why volume of gas molecule is not negligible. So less volume is available for molecular motion. This is the way why the real gas show deviation. Now how it deviates, we look here. If you plot the pressure versus volume, this is graph. We know that the Boyle's law is what? As the pressure increases, the volume decreases. The pressure of gas is inversely proportional to the volume. Therefore, look here, the ideal gas and this is the real gas. What happens at high pressure? Look here, at high pressure, this real gas having that particular volume. Do you understand? So, this volume is as compared to this. Do you understand? So, in real gas, volume is more. Do you understand? VR is greater than this is the ideal gas. Now, at high pressure, the real gas is having this is that volume. Do you understand? So, this is that just from ideal gas increased volume deviates. So, that is the positive deviation at high pressure. This is the just positive deviation. More volume increase volume. But at low pressure, what happens? Look here, at low pressure, this is that real gas. Do you understand? Real gas, the way of that just comes right like this. So volume is here less volume. Volume is decreases as compared to that particular the ideal. So therefore, negative deviation just here and just that is the positive deviation at the high pressure. At low pressure, negative. So this is the way of that the deviation from that particular ideal behavior of that real gas. Now, next point is that compressibility factor Z. Now, this factor Z is useful for to decide how the deviation of that gases takes place from that ideal behavior. Now, real gases show ideal behavior when pressure approaches zero. Understand? Real gases show ideal behavior. But pressure is to zero, that is too small, that is a zero. Now, deviation from ideal behavior can be measured in terms of this particular compressibility factor that is Z. Okay. Now, what is Z or compressibility factor? Z is the ratio of product of pressure and volume and N into R into P. Therefore, Z is equal to what? Z is equal to P into V divided by NR, or Z is equal to what? V real divided by V ideal volume. Do you understand? If here Z is equal to 1, so that time it is an ideal behavior, ideal gas behavior. Do you understand? So this is way of that. Now look here, for ideal gas, we will see again in detail. Z equal to 1. That at all temperature and pressure, that time the gases is the ideal gas. Now, if Z is greater than 1, so that time the gas shows positive deviation. Okay, just you are seeing in that graphical representation how the real gas deviates. So the deviation that is two types, positive deviation and negative. So therefore here Z is greater than 1, so that is positive deviation. And volume of molecules here cannot neglect. Okay, and gas is difficult to compress. Compression of that gas is difficult. Okay. Now, if Z is smaller than 1, so that time is a positive deviation. That gas shows positive deviation. But at low pressure, very low pressure, that time gases have Z equal to 1 or Z is smaller than 1. So that time molecular volume is negligible. You understand? Molecular volume that time is negligible, and the way that time gas can easily compress. Okay, when Z is equal to 1 or Z is less than 1. Why? Molecular volume is negligible, therefore gas can be easily compressed. You understand? And the gases show now ideal behavior. So this is Z is equal to 1 or Z is less than 1. But condition is this: lower pressure, that time gas shows ideal behavior. Okay, this. Hello student, today we are going to study the liquid state. The states of matter. In this topic we have given especially the liquid state and the gaseous state. You know that liquid state is the intermediate state between that solid and that gases. Okay, so therefore intermolecular force of attraction intermediate between that solid and gas. Okay, so intermolecular force of attraction is less than this solid but greater than that particular gaseous state. So intermolecular force of attraction, that it decreases the way of that solid, liquid, then gas. Now the liquid substances shows certain characteristic property like density, volume, vapor pressure, surface tensions, viscosity. Okay, these are certain properties. Now we see this first property. We study this is the vapor pressure. Now look this vapor pressure, how this is the way of that here. Look this diagram. In this diagram, this is the liquid is closed with that particular vessel. This liquid here closed with that particular the container or that vessel. Now the liquid is in this beaker, that is evaporates. Okay, the liquid molecules have tendency to escape that surface. Okay, the molecules have tendency to escape from its that surface to convert into that vapor. That is called as evaporation. Now at equilibrium what happens? The rate of evaporation is equal to the rate of condensation. Means the some molecules get evaporate, and that same time some molecules they want to get convert into its liquid. That is called as condensation. Vapor convert into that liquid. So that is condensation. Therefore at equilibrium rate of evaporation is equal to the rate of condensation. And therefore the vapor pressure is nothing but the pressure exerted by the vapors in equilibrium with the liquid. It's called as the vapor pressure. Okay. Now vapor pressure is directly proportional to the temperature. As the temperature increases, vapor pressure that also increases. Now vapor pressure is inversely proportional to the intermolecular process of attraction between the molecules. You know that for example, petrol evaporates quickly than oil. You know that in petrol the intermolecular force of attraction is very less. Therefore, that will be evaporates quickly. So this is the way of that relation inversely proportional. Now the vapor pressure is inversely proportional to the boiling point. This is again very important key point. This is key point for that different problem or question solving. Vapor pressure inversely proportional to the boiling point. Okay. Now the vapor pressure is generally measured by manometer. This mercury manometer. Look here in this diagram. This is the manometer for measuring the vapor pressure. So this manometer is the instrument in which that the pressure acting on the column is that measured. Measuring the pressure acting on that particular tube. So in this U-shaped tube. Okay, so most common unit useful for that the vapor pressure used, that is the torr. 1 torr is equal to 1 millimeter height of that particular mercury. Other unit is also just like that 1 atmospheric pressure, atmosphere, barometer, or centimeter mercury, millimeter mercury, millimeter height of that mercury. These are the other units. Okay. Now the next point is surface tension. Now liquid shows this another characteristic property, surface tension. Now look here this, the phenomena such as capillary rise of liquid, ink in capillary, and spherical shape of liquid drops. These are due to the property of liquid, and that property is nothing but surface tension. Okay. Now look here, come to in this diagram. So this is in beaker and containing this particular suppose liquid, say water molecules like this. Now look here in this that the water molecules, how this is the way. This is the surface level, surface part. Molecules are present on the surface, and these are the molecules in the bulk. Okay. Now molecules in the bulks, they are equally attracted to the another molecule. That's why molecules in the bulk, here the balance force. Do you understand? So net force is here, that is 0. But what happened? Molecules on the surface. So above portion there is no molecules. Molecules is present only the interior portion, interior part. That's why molecules on the surface here, they are not the equal force. Okay, to understand, they are imbalanced force. That's why molecules here, that is on the surface, they are not that particular the equal force. Above portion is the empty. That's why the interior portion, only downward direction, this interior portion, that force is present. So this is imbalanced force. Okay. So therefore, molecules on the surface, they are under tension. The molecules on the surface, they behave as a stretched membrane. So that's why the surface tension is defined like this. The force acting per unit length perpendicular to the line drawn on the surface of liquid. Understand? This is the force acting per unit length perpendicular to the line drawn on the surface of liquid. That's why the surface tension is the way of that. Another point is like this. Surface tension is directly proportional to the temperature. As the temperature increases, surface tension decreases. Why is this happening? Because the temperature increasing, kinetic energy of that molecule increases, and if the kinetic energy of molecule increases, the attractive forces between that molecules decreases, and of course therefore surface tension decreases. Now second, intermolecular forces is the same way again, that intermolecular forces, surface tension directly proportional to the intermolecular forces. Now the units, SI unit of the surface tension is Newton per meter or Newton meter inverse. Now the general application, surface tension generally useful in that cleaning action of soap and detergent. Okay, so by lowering that surface tension, the water molecule penetrates to that particular oil, the mud in that present in that cloth. Therefore, that the easily washing of that cloth taking place by lowering that surface tension. And same way, the efficiency of toothpaste, mouthwashes, nasal drops, these are the efficiency are also increased by lowering that the surface tension. This is the way of that. Now the next point is that viscosity. This is last point given in this textbook copy. This is that chapter, the topic states of matter. So what is viscosity? It is the force of friction between the successive layers of flowing liquids. Understand? When the liquid is flow, that time force of friction present between that successive layers. You understand? So, in short, what is viscosity? The in short viscosity is the resistance to the flow of liquid, or it is the resistance, flow of resistance of that liquid. You know that viscosity. For example, oily substances are more viscous than suppose that water. Honey, you know example honey. You know, honey is the viscous, or sulfuric acid is a viscous liquid. Now, for explanation, come to this diagram. So, suppose consider the liquid flow through this pipe. This is the pipe, and liquid is flowing like this. So, that time what happened? In central portion of this pipe, central region, this region, the liquid layers having high velocity. Do you understand? Liquid layer having high velocity, but the layers along with the inner walls, they are in stationary. You understand? They have not that velocity as compared to this. They are just remaining stationary. Okay. Now when actually liquid flows through the pipe, then force of friction between the layers takes place. The opposition of that the motion of layers takes place. And therefore different layers of liquid flow with different velocity. That is called a laminar flow. You understand? This laminar flow is present here. So this is just viscosity is like this. Now, therefore viscosity is present in the way of that like this. You understand? Now what is the next point? Viscosity is directly proportional inversely proportional to the temperature. You understand? As the temperature increases, viscosity is the decreases. Now, the larger molecules, more viscosity, more viscosity. Spherical molecules, they having less viscosity, and greater viscosity, the flow of liquid is the slower. If the viscosity is more, then the rate of flow of that liquid is slow. You understand? This is it. Now, come to here that the unit, generally SI unit of viscosity is expressed in coefficient of viscosity, and that coefficient of viscosity is nothing but eta. This is called as eta generally. The symbol is eta. Now eta is this is that SI unit for that Newton second per square meter inverse. Do you understand? Newton second per square meter. This way. How this is that the unit is derived? You know that the force of friction between the successive layers. Therefore, force is directly proportional to the area and velocity of that liquids, and x is the distance. You know that successive layer. So distance. So therefore, eta is equal to force into distance divided by area into velocity. If this is that taking this here, fix of unit, force is expressed in Newton, distance is in meter, area is meter square, and velocity is meter per second. What is velocity? You know that rate of change of displacement in unit time. That's why unit is that meter per second. So if you getting this cancelled, meter, so what is remaining? Newton second per meter square. Okay, so that's why this is the SI unit of that viscosity. Now in CGS units, this is generally expressed in poise. So 1 poise is this. Do you understand? 1 poise is here, is this. 1 poise is equal to 1 gram centimeter inverse and second inverse, or this is converted into kilogram, 1 kilogram meter inverse second inverse. This is the poise unit. Poise is scientist, after the scientist name given that the poise. Okay, this is the way of that. Now illustration. What is that? The example. How will you illustrate that viscosity? So like this is that lubricating oil. You know that lubricating oils, that is quality. How to maintain that the oil generally here that necessary good quality. So good quality in that the lubricating oil, no change viscosity. You understand? There is no change in viscosity. Now, in increase in blood viscosity, you know, in human body the blood increase viscosity, blood is more viscous, that time what happened? The cardiovascular disease, that is symptoms, indication of that, the cardiovascular disease. Now, glass pans of old buildings, after some time, more time, so at the bottom of that pans, that will be become more thicker. So indication is not, glass is not a solid, but glass is a super cool liquid. Okay, this is way of that viscosity. Thank you.